Hi, everyone. So let's welcome everyone back after the break. This next section will be a little bit easier since it's largely a review of material we've already covered, which is modular powers and squaring to get answers. So you guys already did the baby version of this on the midterm. We're just going to be taking this one step further. So let's remind ourselves, what are exponents? So we've been through this many times now, but exponents are repeated multiplication. And in the ordinary integers, these get big really, really fast. So if you want powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on, right? So powers get big really, really fast. Exponential growth is scary for many reasons. Let's also do 3. So 1, 3, 9, 27, 81, 243, 829. So 3 grows even faster than 2, as you'd expect. Okay, so in normal arithmetic, exponential growth makes things get big super, super, super fast. But now, in modular arithmetic, the powers bounce around the circle because things can't get big. You can't get far away from your starting point in modular arithmetic because you're just going around in the circle. Like maybe you're going around the circle really, really fast, but you're still just going around the circle and you're never going to get too far away. So in base 12, so let's see, in base 12, because we have a clock on the right, well, what are the powers of 2? Well, 1, 2, double that. So multiply by 2, so you get 4. Multiply by 2, you get 8. Multiply by 2, you get 16, but 16 is equivalent to 4. You multiply by 2 again, you get 8. You multiply by 2 again, you get 16, but that's equivalent to 4, and so on. So you notice that it does bounce around, but in this particular case, it seems like once it bounces to 4 and 8, it just keeps on swapping between the two. And let's see what happens for 3. 1, 3, 9. 9 times 3 is 27, right? But 27 mod 12 is just 3 again. So you end up getting the same behavior where you keep on bouncing back and forth. Now, as a mathematician, one of the questions we'll be addressing later is how do you know what sort of patterns happen? Well, that's the later part of the lecture, which we may or may not get to today. For now, let's just try to figure out how we're going to quickly compute it. So let's ask a question. You guys all did this on your midterm, so hopefully you'll be able to answer this. How many times do you have to multiply 2 numbers together to figure out 2 to the 16? Okay, so we're getting a bunch of answers for 4, and that makes sense because I already taught you this method. But let's just recap it again. So if we had 2 times 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 2. If you did this the stupid way, you would get 15 multiplications, right? 15 multiplications. Because you could just keep on multiplying, and that will get you the answer eventually, because that's how powers are defined. But you can be faster. So one faster way is to notice that this is 2 groups of 2 to the 8. 2 to the 8. And so if you were to group it together in that way, that would be, well, 7 multiplications to get 2 to the 8, and then 1 multiplication to get, or to do 2 to the 8 times 2 to the 8. And so a total of 8 multiplications. But of course, we had an even faster way that we discussed before the midterm, which is you'll notice that this is also 2 to the 2, to the 2, to the 2, to the 2. And so you could just do 2 squared is equal to 2 times 2. 2 to the 4th is equal to 2 squared times 2 squared. 2 to the 8 is equal to 2 to the 4th times 2 to the 4th. And 2 to the 16 is equal to 2 to the 8th times 2 to the 8th. So you only need 4 multiplications. Okay. So this is what we call a method of successive squaring. We didn't give this a name earlier, but one name is a successive squaring for any x to the n if n is a power of 2. So 16 is a power of 2. Well, we can quickly compute it by repeatedly squaring. So for example, if you wanted to compute any power of 3 that is a power of 2 power of 3, so you can quickly get 3 to the 3 squared, 3 to the 4th, 3 to the 8. Oh, sorry. I think by power of 2, yeah, 3 to the 16, 3 to the 32, and so on, right? So just as an aside, for those of you who are interested in this kind of thing, the total number of multiplications this uses is log 2 of n multiplications. So don't worry, we're not going to talk too much about logarithms for now. And I don't actually know if we get to too many logarithms in this class, but just for those of you who are interested, this is basically logarithms. But now, if n is not a power of 2, well, one thing you could do is you could rewrite it as a sum of powers of 2 and then multiply them together. So what do we mean by that? Well, if you had 3 to the 23, you know that 23 is equal to 16 plus 4 plus 2 plus 1. And so therefore, 3 to the 23 is equal to 3 to the 16 times 3 to the 4 times 3 to the 2 times 3 to the 1, right? You just add them together or multiply them together and you have the answer. And how do you break them up? Well, you just repeatedly subtract the largest power of 2 that's smaller than the remaining pieces. So for example, 23 minus 16 is equal to 7, 7 minus 4 is equal to 3, and 3 minus 2 is equal to 1. And so the pieces that we care about are the 16, the 4, the 2, and the 1. Okay, so you break it up into pieces, and that allows you to use these, and you can then multiply together. So let's try it out. And I have given you a table of the powers of 2 in ordinary arithmetic. In this particular case, I think I will give this to you on future exams, so you don't need to memorize powers of 2. Although, if you're going to continue on in math or computer science, you probably should memorize powers of 2. Like, they're super useful. But for now, I will give them to you. So let's compute 7 to the 42 mod 11. And these are your possible answers. Oh, can I go back to the previous slide for a second? Yes, sure. So basically, it's a 3-step process. You break up the exponent into a sum of powers of 2, and then you have to construct each of those powers of 2 and then multiply them together. And so we're doing 7 to the 42 mod 11. And I'll hang out on this slide for another couple of seconds. So for the record, we're doing 7 to the 42 mod 11. That's what we're trying to do here. Oh, sorry. Okay, so let's switch back. So let me go ahead and give you the first step, which is 42 minus 32 is equal to 10, and 10 minus 8 is equal to 2. And so notice that we have powers of 2, the 32, the 8, and the 2 here. And so what you want to figure out is you want 7 to the 42. You know that's equivalent to. One other thing I should mention is that the method I gave you for successive powers of 2 works for both ordinary arithmetic and modular arithmetic. It works for both. We're obviously focusing on modular arithmetic in this part of class. But that's going to be equal to 7 to the 32 times 7 to the 8 times 7 squared. Yes, exactly. So I chose 32 because it's the closest to 42 that's smaller than it. So if you don't choose the right one, you'll still eventually get the right answer, but you'll just do more work. So if I chose 16 instead, well, then I would need to choose 16 again. And you still can get the answer from that, but it just takes more work. So you could do 32 minus 16, which is going to give you 26, minus 16, which is going to give you 10, minus 8, which is going to give you 2. And then you'd have to multiply together all of those powers. But so now you just need to solve for at least 3 things, and you know how to do that because those are all powers of 2, and you can compute those. And so basically what we need to figure out is we need to figure out 7, 7 squared, 7 to the 4th, 7 to the 8th, 7 to the 16, and 7 to the 32. Those are the things you need to figure out in mod 11 arithmetic. Okay, we have a few answers, so let's start working through it together. So that's 7 is just 7, of course. 7 squared is congruent to 49, which is going to be congruent to 5, right? 7 to the 4th is going to be congruent to, so we have a lot of people who are guessing A. Hopefully you guys actually solved it and are not just going by whatever the first person answered, but let's see what happens. 7 to the 4th is going to be congruent to 25, which is congruent to 3. 7 to the 8th is going to be congruent to 9. 7 to the 16 is congruent to 81, which is going to be congruent to 4. And 7 to the 32 is going to be congruent to 5. So which ones do we have? So substituting those in, we have 32. So that's 5 times to the 8 is 9 times 7 squared. That's 5. And so that's congruent to 25 times 9, which is congruent to 3 times 9, which is congruent to 27, which is congruent to 5. And so the answer here is actually C. Does anyone have any questions about that? Since it seemed like people were struggling a little bit. Yeah, what's up? Sorry, what was that? Yes, absolutely. Let's try another one. So let's try computing 11 to the 55 mod 19. Let me zero that out. So again, there are basically 3 steps. One is you figure out how to break up 55 into a sum of powers of 2. Then you have to compute the powers of powers of 11 to powers of 2. And then, well, then you multiply them all together at the end. So let me go ahead and start by just subtracting. So 55 minus 32, well, that's going to be equal to 23 minus 16, that's going to give you 7. Minus 4 is going to give you 3. And minus 2 is going to give you 1. And so the powers that you care about are this one, this one, this one, this one, this one. And what you need is you want 11 to the 55 is congruent to 11 to the 32 times 11 to the 16 times 11 to the 4 times 11 to the 2 times 11. And I think I will give you guys a moment to go through and compute that now. So one other thing I should emphasize is this is one particular way of breaking up these powers. You could break it up however you wanted to. If you want to, you could compute 11 to the 10 and then do 5 of those, and then another 11 to the 5. This is just one particular method that will get you, that will work for any number, but there are other methods that will also work. And then how did you break down 55? Well, you just keep on subtracting out the biggest power of 2. And so the biggest power of 2 that's smaller than 55 is 32. And the big, so that gives you, you're left with 23 of them. So let me actually write that out a little bit more So after you take out this piece, then you're left with 23. And then you keep on taking out powers of 2 until you're left with, well, just the, yeah. Okay, so it looks like people got an answer for this one. So let's check it out. So 11 is congruent to 11, easy. 11 squared is congruent to 121, which happens to be congruent to 7. So you can do the division and then figure that out. Then 11 to the 4th would be congruent to 7 squared, which is congruent to 49, which is congruent to 11 again. Why is there an extra 11 at the end? Because what you need is so the important thing is you need 55 is equal to 32 plus 16 plus 4 plus 2 plus 1. Okay, so really all we're doing is we're breaking it up into some sum. And so you need this to be true. And so there's a 1 at the end because you had 1 left over. Why is 11 to the 4 the same as 7 squared? Okay, so let's write this out in a little bit more detail. 11 to the 4 is the same as 11 squared squared, right? 11 squared squared is the same, 11 squared is the same as 7, so that's the same as 7 squared, which is the same as 49, which is the same as 11. And we also have, when we have 11 to the 8, well, wait a moment. So 11 to the 8 is just 11 squared then. So that's then just 7. And 11 to the 16 is going to be 11 again. And 11 to the 32 is then going to be 7 again. And if you plug all these things back in, what you end up with is 11 to the 7, 32 is just 7 times 11 to the 16 is 11 times 11 to the 4 is 11 times 7 times 11. When you multiply this through, you end up with, well, you have 7 squared times 11 cubed. But 7 squared is, of course, 11 again. So this is just 11 to the 4th, sorry, 11 to the 4, which is just 11. So the answer here is C. Okay, it looks like most people got that. Let's try one more just to make sure we're all on the same page. And then I think that will be it for this mini section. So let's compute 3 to the 1,300 mod 100. So this one's going to be a lot more computation. The breakdown isn't hard but the actual like repeated squaring will be just because these are pretty big numbers. And one of the questions we'll be asking us is this the most efficient way of doing it, or are there even faster ways, which we'll be discussing in the next section. One of the sort of key points I want to emphasize about many of these problems is there are slower and faster ways of solving problems. You'll get the same answer if you do it a slower way, but sometimes, and so if you don't remember the faster way of doing it, you can always fall back on the slower way in theory. For assignment 4 and quiz 4, will you provide pairs of 2 charts? So I will go ahead and provide pairs of 2 charts for the remainder of, for any time I think it's necessary, I will provide pairs of 2 charts. When we try to break down the exponent, should we always start with the power of 2 that's closest to the exponent? Yes, that would be my suggestion. So the real answer is you can break it down however you want, but I find it easier if you break down the closest one, but start with the closest one. So for example, 1,300 minus 1,024, 276. And then the next closest one would be 256, which gives you 20, minus 16, which gives you 4. And so here, those would be the pairs that you'd want. So what you end up with is 3 to the 1,300 is congruent to 3 to the 1,024 times 3 to the 256 times 3 to the 16 times 3 to the 4. Oh, sorry. And obviously this chart is going to be a little bit longer because you need to get all the way up to 1024 because we ended up with one really big number. Okay, we're starting to get some answers strictly, and so I'll start working through it. But so we have, would you subtract 2 from 4? So the point is, once you get to a power of 2, you don't need to, because the whole point of this breaking things up is to try to get it so that you have only powers of 2, because the chart we're about to make is going to give you all the powers of 2, right? So 3 to the 1, 3 to the 2, 3 to the 4, 3 to the 8, 3 to the 16, 3 to the 32, 3 to the 64, 3 to the 128, 3 to the 256, 3 to the 512, and 3 to the 1024. So can you subtract 2 from 4? Yeah, sure, you can, but it's not going to do you any good because we're in order to get the powers of 2, we're already going to get 3 to the 4 anyway. So there's no point in breaking it down further. Okay, we have a lot of A's, so we'll see if that's right. So that's 3, right? And that's equivalent to 9. That's equivalent to 9 squared, which is 81, right? And that's equivalent to 81 squared, which is 6,561. But I did mod 100 to make life a tiny bit easier. So this is just 61. So this is 61 squared, which is 3,721, which is just 21. This is 441, which is just 41. This is going to be 1,681, which is just 81. But no, but it's starting to repeat again. So if we have 81, the next one is going to be 61, the next one's going to be 21, the next one's going to be 41, and the next one's going to be 81. Okay? And so then once you've done that, then all you have to do is then you just multiply back through. So this is equivalent to 81 times 21 times 21 times 81. Well, note that 81 times 81 is going to give you 61, and 21 times 21 is going to give you 41. And so this is 2501. So this is equivalent to 1. And so yes, people were indeed correct. Okay, so this is one method of solving for arbitrary powers, and this will always work. So if you forget everything about the next method that I'm going to teach you, you can still fall back on this one.